So good afternoon. We are here to present a smart FPGA-based machine vision system. If anyone is curious what an FPGA is, it is a field programmable gate array. So it's basically hardware that we're going to use for our software side. We're going to talk today about our project motivation and description, our societal impact, our system description, the related theory behind everything, our system module description, iterations and testing analysis, our project status and future work, the cost analysis behind it, our applicable ethics and standards, and of course our conclusion and some references. Our team consists of myself, Dominic Beaumont. I'm an electrical engineer. I was a team leader, and I was on the software design.
Anthony Valenti, I'm an electrical engineer, part of the hardware design and software research.
Michael Scuozo, I'm an electrical engineer, part of hardware design and hardware research.
Allison Danforth, I'm an electrical engineer, and I did hardware design and market research.
I'm James Durkin, I'm the head of hardware.
And my name is Dominic Dominguez. I'm a computer engineer, and I will lead software design and software research.
So for our project motivation, object recognition has become a very, very popular thing in today. So we wanted to come up with a low-cost, high-efficiency way to integrate object recognition at very fast rates into existing manufacturing facilities. So what we came up with was our FPGA-based one.
So our project is an FPGA-based smart machine vision system that has the ability to detect objects as well as their defects in a given industrial and manufacturing environment. And what we're looking to do is flag these objects for defects and then send a signal to our conveyor belt to tell it to stop operating.
Okay, for our societal impact, image recognition is being used right now in a variety of different sectors, but our main focus is on how it benefits manufacturing industries. So some of these benefits is that it provides efficient automated solutions to streamline some of their processes. It also allows for easier system integration within the existing manufacturing setting. It also increases quality safety control while minimizing human error. Image recognition is being able to detect an image a lot faster than the human eye can. It also increases skilled labor. Based on the software we're using, we're all creating jobs for higher skilled labor, and it also increases productivity. But our main concern with quality control is that we want to be able to detect these objects as fast as we can, so that manufacturing companies delivering safe and reliable products to their customers.
We're going to go over the system description. So on the front end, we have our conveyor belt, which represents an industrial setting for typical industrial applications. And as Mike touched on before, we're trying to detect defects for our objects. So once it detects a defect, it then goes into the Ultra 96, which then utilizes an object classification program to determine a defect. And once it does detect this defect, it does trigger a GPIO pin to our 3.3 volt relay, which is in series with our motor and thus stopping production. And we want to do this so that way we have to warrant human intervention when we detect a defect in our system. And on the back end of our system, we have the Ultra 96 connecting to an output via USB, so that way anyone can plug in with a laptop or PC so it can make adjustments to our object classification program. And also on our back end, we are using a power supply to power both the Ultra 96 and our motor as well.
Okay, for our related theory, this is associated with us using TensorFlow. Our TensorFlow algorithm is using a deep learning neural network, and with this neural network, it allows us to group unlabeled data with similarities based on our input examples, and then allows us to classify the data once we have a labeled data set to train on. But because we're using a predefined data set with COCO and TensorFlow, we didn't actually have to train our images, but this is something that will be discussed in our future work. These are some of the formulas and equations that are associated with building a neural network, such as the cost function, backpropagation, forward propagation.
So for our mechanical design, we started off last semester using a wooden small model for our conveyor belt. And then this semester we wanted to build a sturdier one and a more professional one for our testing and for our project. So starting on the left-hand side, you can see we put it together using metal brackets for the frame. Moving over, you can see we use PVC pipes for the rollers on the conveyor belt. And then at the extreme right, you can see the belt is tightened and fastened. and the motor, you can also see in those pictures as well.
Okay, for our mechanical testing, once the belt was designed and built, we wanted to manually operate our belt to make sure that there's no defects or anything that would go wrong with it. As you can see, we're utilizing our power system, our relay, and our buck converters, which are in our 3D printed model case. And this is where we were able to figure out anything that went wrong with the belt before integrating it with software.
So for the hardware side, we did unit tests to ensure our quality of our hardware before we integrated it into an enclosure. So for the first thing that we tested was our power supply, and the main thing we wanted to test for our power supply was load regulation and the voltage ripple, since this is a very important and essential task in industrial applications. We want to make sure there's no hiccups in our power supply. And if we look at the results for our measured outputs, we checked that they were well within the range that we set, and they all passed with flying colors. And in addition to this, before we started installing our hardware into the enclosure, we want to make sure that all parts of our system work together before we seal up the box. So, and we also utilized an integration test to make sure sequentially, as the operator is using this system, everything works as intended in order. So the first step is turning on the power supply, and the buck converters turn on as well, which passed. We then turn on the Ultra 96, and at this point in time, we utilized an Arduino since we didn't have the GPIO pins working for Ultra 96 to simulate an e-stop. And in addition to this, we also sent voltage signals to our relay to simulate an object classification detection of a defect, and with pacifying colors. And for the last part, we took the voltage ripple measurements, and we made sure that they were well below 1% voltage ripple of 120 millivolts, since we're working with a 12-volt power supply. And these can be shown here on the oscilloscope. As you can see here, according to the parameters for this, it is well below the voltage ripple of 50 millivolts. And this is for the motor as well, which is also well below the 50 millivolts as well for our system.
So for our hardware design, we want to make everything into a nice, easy enclosure that you don't have to hire an electrician to wire, that you can plug everything in from the outside. So this is pretty much the design that we came up with. The enclosure should meet all UL 508 industrial control panel specifications. Most manufacturing facilities we looked into, they kind of require your product to be UL listed. So we wanted to make sure that anything that we design can meet those specifications if it's designed and built. So we're going to utilize your typical 120 volt, 15 amp switch input power. The adapter that we used also has an integrated 5 amp slow low fuse for safety. We also have an integrated normally closed e-stop and reset switch, which can be seen on the top left there. So in case there is ever a crisis in a facility, someone can hit that switch, it's bright, it's right where it needs to be, and the whole system will stop basically immediately. We also have a manual override button to drive the relay or the optional I/O on it, on the enclosure. We also incorporated just some status LEDs, so someone that's just possibly walking by can see the status of it. We have a green DC power to signify that our inverter and power supplies and buck converters are all working correctly. We have a red fault LED, so if the system stops working or the relay trips, obviously the belt will stop, but you can see that there's a problem in the enclosure itself. And then we have a blue run and enable status light. On the other side, we also have two panel mount USB type A's, which can be used to install a USB line camera or any other USB camera or optic sensor that someone desires, along with using it for a programming port if need be. And then also on the bottom, there's expandable panel mount I/O that integrates into existing manufacturer controls. So it doesn't matter what the logic level of the facility uses. If it's 24 volt logic to control their motion controllers or industrial drives, we can do that by using the relay as a switch. If it's 12 volt, we use 12 volt. So we kept our options open to be relatively universal.
So some hardware iterations that we had to go through was looking at conveyor belt. We went from a wood design to a metal design. We also added additional brackets with bearings and tensioners for more stability. And we also added grip tape to
here, this is the functional diagram for the Ultra 96. As you can see, like most microcontrollers, it utilizes a system on chip. But the benefit to this board was that it has programmable logic associated with it as well. So any CPU, like high CPU demanding process that image recognition kind of involves, we can offload that into programmable logic, which is hardware acceleration, and get results much faster, and then send that information back into the software and the program.
So this is our software unit test of the Tiny YOLO object recognition algorithm. This was used on the Ultra 96. So what it does is it takes into account the entire image and it runs it through a single neural network called the darknet. And then from there, it divides the image into 4 quadrants, and from there it starts to predict what it is and predict the object detection. As you can see here, the software unit test for the performance results, the hardware accelerated Tiny YOLO object recognition was 3 times faster than the same object identification algorithm run in the software. The execution time for the hardware was much faster than the software, and then the hardware accelerated process was able to perform over 4,000 MOPs, million operations per second, while software wasn't even capable of 1,000.
So after we got our object recognition software to work and we were able to accelerate with the hardware, we went to try and integrate this into our existing enclosure and everything else. But as great as the Ultra 96 does, as a job as it does involving the hardware acceleration for object recognition, it being such a new board, there's limited documentation for it, and we had a very difficult time accessing the headers and the GPIO pins on it. We had some back and forth with the company, AveNet, that creates it. We tried to go back and forth between some other individuals who've done some projects with it. But unfortunately, we weren't able to get it to work or get the GPIO pin on the board to function as correctly. So to move forward in a contingency plan, we tried to do the object recognition via a Raspberry Pi, just because there's plenty of documentation for it. It'd be pretty simple to set up, and also we were ahead in hardware, so we had the availability to try and do that as we tried to troubleshoot this current board.
So here's our software iterations. First on the Raspberry Pi board, we started off with the TensorFlow neural network, and from there we attempted hyperthreading to increase the FPS on the board. We ditched the USB camera that we were using on the Ultra 96 and went for an integrated Pi camera to increase the FPS. And ultimately we ended up with a utilized and optimized OpenCV by using a virtual environment and using color thresholding to identify object detection while having complete control of the GPIO. So in that case, we did not go with the neural network and instead opted for the color thresholding because it had complete control of the GPIO pin. For the Ultra 96 board, we started with the Sobel and Candy edge detection to test image processing techniques with software and hardware. Then we attempted to apply the object detection with the QNN or a quantized neural network dataset that was available on the board. But ultimately, we decided with the Tiny YOLO that implemented and performed the object detection and classification using the darknet neural network and hardware acceleration.
Okay, so for our testing analysis with TensorFlow, as Dom mentioned before, we want to take into consideration that using TensorFlow on the Raspberry Pi was our plan B option, and we just started working on that 3 weeks ago, so we made significant progress since then. As for our unit test, we wanted to make sure that TensorFlow would actually recognize an object, which it did on the top left. It was able to pick up the bottle, draw a box around it, and label the percentage of how well it's recognized an object. For our integration test, we wanted to make sure that we were able to enable the GPIO pin to activate the relay. And as you can see up top, the blue light is indicating that the relay was initiated, and the red light tells us when the relay was off. And for our acceptance test, we wanted to incorporate everything. So we have the live video feed working with object recognition, being able to detect an object while operating the board and enabling the GPIO pins to activate the relay.
So for our future plans, we plan on designing the software for the Ultra 96 board, as well as train and create a custom data set for the through was designing the belt. Because of because our background isn't in mechanical design, we didn't really have much guidance with that, so we kind of built it from scratch without any knowledge on that. We also want to, another challenge was enabling the GPI tokens on the Ultra 96 board. And another one was activating the hardware using object recognition techniques. For the software component, we have compatibility issues with the Ultra 96 board and limited documentation with it. And we also wanted to make the frame rate per second faster on the Raspberry Pi, which we didn't get to do.
Right, so the lesson learned in this project was, the first one was Python, because all of us did not know Python, so that was one of the new programming languages that we learned doing this project. Another one was enclosure design, so having to design and organize all the stuff within the enclosure. Time management, which is like delegating tasks amongst the 6 of us, and troubleshooting techniques.
So further requirements that we can utilize if we're going to actually make this into a valid product that we want to sell on the market is we want to include a PCB design. Instead of buying all these individual components, which are very expensive, we can compact it, make it smaller, make it into a shield for a Raspberry Pi or Ultra 96, where all we have to do is just plug it in. And this will increase our productivity reliability, since we aren't just using jumper wires, which are more prone to error and human error. In addition to that, we can just offship this PCB code to any company so that we can manufacture it very quickly, very efficiently, very economically. And we also, including this, we want to add connection ports on the board. So regardless if you use like a different sort of camera, we want to add more options for our clients so that way they can put in their different inputs and outputs depending on whatever hardware that they use for their system. And finally, we'll want to include custom labels for our product as well. So if a technician or a worker utilizes this, it will be very easy to use so we can minimize downtime and continue improving production down the line.
So taking a look at our cost breakdown, starting at the top, the Ultra 96 was a tremendous help for us because that was provided to us through Manhattan College. So that was a fixed cost. So taking a look at the bottom, if we had to pay for the Ultra 96 out of pocket, it would have been approximately $429 for the project. But since we didn't have to, our project cost came out to approximately $180, which is way under budget.
Some standards and constraints that we have to go through with the IEEE 802.11b for the Wi-Fi, the National Electric Code, the 2 USB 3.0, 1 USB 2.0 Type A, UL 508A standard for industrial control panels, the constraints were the time and cost requirements, the databases that was to be used, and the language requirements and communication protocols.
From an ethics perspective, claims being made as to what our project is capable of. This was extremely important in our case, as we were working with the Ultra 96, which is a relatively new board, and so there's not much documentation on it, and so we were very upfront about what we can and what we could and couldn't do with it. So that was important. What people and things may be captured without our permission. We took a lot of film during our testing, so we were always conscious of what we were recording during our testing. What jobs will be taken away from the industry. In our case, it also creates a lot of jobs from the industry. Being aware of possible existing patents on the project and being forthcoming with those. And then lastly, from the IEEE, to hold paramount the safety, health, and welfare of the public, and to let them know if anything is in danger.
Okay, so for our demonstration video, there's 2 parts to the video, and these are based on using the Raspberry Pi TensorFlow. So the first part of the video will show us using TensorFlow and how we're able to recognize an object, enable the relay, and operate the board. As you can see here, the bottle's moving, the blue light initiated the relay, and you can also see in the top left the frame rates per second are very low using the Raspberry Pi, but we are able to recognize the image. The second part is using OpenCV with color thresholding, so we chose specific RGB values based on the color green on the labels, and the board is running until the camera is not able to detect the label or the correct RGB values. You can see that it stops here. references that we use to complete our project. Any questions?
A lot of people in your group, how did you divide up the software tasks?
Originally, we kind of started out as we had 3 of us working on hardware and 3 of us working on software. And then as we realized that we were starting to struggle in our software, especially since we're mostly electrical engineers and not computer engineers with a lot of programming experience, as we came to the point that we found we were ahead in hardware, we kind of went back into saying, hey, can you guys work on the Raspberry Pi, because there's a lot of documentation for it, and we'll continue working on this board up until this date. So, like, Dominic and myself worked on the Ultra 96 board for a majority of it, and we learned a lot of Python involved with it. And then after we had a finished enclosure and most of our hardware designed and working and tested, we kind of jumped to everyone else using a Raspberry Pi and seeing how quickly they can develop something, which involved Anthony, Mike, Allison, and James. That's probably it.
First of all, I see the project is practical and applicable. This is a good point. I just have one question. A system, normally a machine vision system, may have issue with multiple variables in the environment, like changing lighting, color, curvature, field of view. So will you guys be able to address this in the detection algorithm?
Yeah, so one of the ideas that we didn't do a very good job bringing up in the presentation is, along with buying the enclosure, you'd probably have to pay for about a week of programming time, depending on the facility, to set up that recognition for the specific facility. So in our case, we used following examples for like a following plant, something like that. Meanwhile, there can be another plant that does PCB design, and they want to check for like a bad solder joint or something like that, to which a specific data set would need to be developed for each, and being able to program that in the environment can help reduce errors.